Okay, open up your notes, page 18. I believe it's 18. Yep. And you guys are doing G. Go for it. The same stuff. You're finding the domain on page 18. And this is our second day of 1-2 notes. This is day 2. I suppose I should change that on my board here. This is day 2, and the things we're going to be running through today. Okay, we're going to talk about determine if functions are continuous, discontinuous, and the type of discontinuity, whether it's removable, non-removable, jump, or infinite. We're going to determine where a function increases, decreases, or stays constant, and we're going to determine if a function is bounded or unbounded. Those are the things we'll be able to run through today. Okay, because of that, there is an extra page of a worksheet that I was going to hand out today about piecewise functions. We are going to do that on Monday. Okay, because I'm going to take most of the hour. I'm not going to give you any time. So your assignment today will be page 94 to 98, numbers 21 to 33. And here on page 18, the things that we did not finish. Okay, and we'll come back to them Monday and we'll finish the last 4. So people are like, what? And I have 20 and 21, but this is 18. I took something out of my stuff from last year. So we've got page 18 only, and we're just going to finish those. Okay, is there any questions? Take a minute and a half and go ahead and do G. So when we're looking at this in G, you got to keep in mind the things that are going to govern your restrictions. First of all, you're all used to having the stuff in the denominator governing your restrictions, okay? But if you look at this and you just say, oh, that's going to be a problem, I look at that and I'm talking about this stuff to govern x squared plus 5 can't be 0. I know that. Okay, but when I solve this for x, I find out that x can't be plus or minus square root of 5. Okay, but now if I plug that back in, will there ever be a 0? Even if I put in negative square root of 5, I square that, that's 5 plus 5, which is 10. So the denominator is not ever going to be 0. That's never going to enter into our problem with being with a restriction. We won't have it. But the numerator, however, the top part of my fraction, that has to be greater, or that can't be 0, and it's got to be positive. So if I'm looking at that and I solve this, opposite of x has got to be greater than or equal to 0, I find out that x is less than or equal to 0 after I divide. Okay, so when I divide, the sense of that sign switches. So now my domain here becomes x such that x is less than or equal to 0. Okay, and if I wanted to look at it, that's my set builder, and my interval notation, that's my domain. Okay, and remember, I'm doing both. I'm showing both notations. You only have to do one when you're asked. I want to make sure you're comfortable with both, so it's something that you can go easily back and forth between. In H, when I'm looking at this, I have no restrictions because of my numerator, the top part of my fraction, okay? But when I'm doing this, I want to make sure you recognize that restriction on the numerator doesn't exist, but my denominator has a problem. So when I run through my restrictions on my denominator, I know that's -3. We're going to pull this down. I put a negative in here earlier and it did not jam. I put it in with my fraction and it kind of became part of my fraction bar. So I'm definitely showing that it's a -3/5, okay, that x squared. Now I'm going to take the square root of that. If I take the square root of that, hey, that's a problem. Or is it? We're talking about real values when we're talking about these restrictions. And right now I'm looking at the fact that I've got the square root of -3/5. Will I ever have to deal with this restriction? No. Okay, so when I'm looking at this one, I know that this is going to be good for all real numbers. Okay, my domain is all real numbers, or my interval notation goes from -infinity to infinity. Or if I wanted to say this, I suppose this also is, I could talk about my all real, x is contained in all real numbers. There, I could write it that way, or as a subset of, okay? Now, the other 4 are part of today's assignment, okay, that are left on this page. So keep that in mind when we're looking this over. Let's go on to our next page. Now, to find the range of a function, look for all y coordinates that correspond to points on the graph. A good approach is to use graphical and algebraic approaches simultaneously. Keeping in mind, you've really got to make sure that your use of a calculator is limited, that you're not really relying on it. You're using it to check your work, not do your work. In a lot of places, especially those gray oval questions in the book. Okay. Now, keep in mind that in calculus, you are often not allowed to use a calculator to visualize the function. So the more we do without it right now, as we wean ourselves off, keep visualizing it, keep thinking about it, check it, and go, oh, okay, all right, and try to reassert your understanding of what's going on with that function if you've made a mistake on it. Throughout the year, you should be able trying to get an idea of the shape of the graph before you grab your calculator. Now, when I do this one, this is an extension of the f of x equals 1 over x. And that graph generally does this. Okay? That's what that graph looks like. Okay? The inverse graph. But now I've got a 2 over the top. So how's that going to change that graph? So when I'm looking at this, I'm thinking that I can't get rid of anything, but I've got my domain. It really is going to work the way it is, but we're going to talk about domain and range. I'm going to look at this graph first. If I plug in 2, I get 1. And if I plug in 1, I get 2. So I've got that part of the graph up there. If I plug in -1, I get -2. Or if I plug in -2, I get -1. So I got this part, this second part of the graph down here. Okay. Now, keeping in mind, there are some other things that we have yet to talk about, but I'm going to put them into this graph because it is something that governs how the graph behaves. There's a vertical asymptote here because x cannot be 0. And as x approaches infinity, the bigger value that I put in for x, the larger the value, the function itself tends to 0, and that's my horizontal asymptote rule. So I'm looking at that as my horizontal asymptote. It'll never cross it. It approaches 0 from the top and the bottom. So that's what my graph looks like. Now, if I'm talking about setting y equal to 0, I get this type of thing. 0 equals 2. Okay, it doesn't make a whole hill of beans sense, but when I have that happening, my y to be 0, it isn't 0, it can't be 0. Okay, but it makes sense that we don't have anything on my y-axis, okay, because it can't be 0. If I look at the idea, my all other numbers, and I plug in k for my y, and I solve for x, I get that x is equal to 2 over k. For any value that I put in, I'm just dividing 2 by that value for my x value. Now my domain. Domain's left to right. Oh, I did have black in. Domain is left to right. It goes this way. These are my domain values. From -infinity to 0, because function doesn't exist at 0. I've got a discontinuity. And from 0 to infinity. That's where I did my domain. My range. My range is about the y value. And I've got some folks that always go, well, where did you get that? My range is how far does it come from and where is it going? Okay, my range is this stuff. So it goes from -infinity, doesn't include 0, to infinity. So I've got to keep that in mind, and that's how my range and my domain have been defined, and I want to make sure that those are clear when we're doing this, that domain left to right, range up and down. Continuity. One of the most important properties of most functions that model real-world behavior is that they are continuous. This means that a function is continuous at a point if the graph does not come apart at that point. Now, simply put, if I have a pencil and I'm able to trace my graph, and I forgot to take care of this, if I'm able to trace my graph without lifting my pencil, my graph's continuous, okay? It's a continuous graph. If I cannot trace it without lifting my pencil, then I have something to deal with. It's either a vertical asymptote, which is a infinite discontinuity, okay? It is a hole where the graph doesn't exist at that spot, which is a point discontinuity or removable discontinuity. And then I have something called a jump discontinuity. Okay, a jump would be a vertical jump in the two graphs. I go from one part of the graph to another part of the graph further up or further below where I was. Okay, so this is continuous in all x, this graph. Now, this graph is continuous everywhere. Notice that the graph has no breaks. This means that if we were studying the behavior of the function f for x values close to any particular real number a, we can be assured that f of x values will be close to that f of a. Actually, we'll run right over it because there is no concern about us not being able to find f of x for the value of a and find the value of f of a. Now, here, I'm comparing these two graphs. These are removable discontinuities. Okay, one has a point that has been redefined, f of a, it's like way up there. Another one doesn't, but these are both removable discontinuities. And both are discontinuities because if I was going to trace it with a pencil, I'd have to lift it to continue my graph. Okay, this graph is continuous everywhere except the hole at x equal a. If we are studying the behavior of this function f for x values close to a, we cannot be assured that the f of x values will be close to f of a. Okay, and in this case, f of a is way up here. Okay, from the left, from the right, we approach this a, and all of a sudden, boom. That's what they're talking about. Can't be close to f of a as we approach from the left and the right. Now, in this case, f of x is smaller than f of a. For x near a, this is called a removable discontinuity. Because it can be patched by redefining f of a so as to plug the hole in a way, but it's called removable. Okay. And this exists because there's a hole in the graph. Okay. Now, the next graph is also removable discontinuity at x equal a. If we were studying the behavior of this function, f for the x values close to a, we are still not assured that f of x values will be close to f of a, because in this case, f of a doesn't even exist. It is removable because we could define f of a in such a way as to plug the hole and make f continuous at a for that function. We could just say, hey, it's going to be this. But in this particular case, keep in mind, that's the picture of what removable discontinuities look like. And we'll talk about holes in your graph. For this next one, going with my pencil thing. And, ooh, I forgot to pop that open. That's just a removable discontinuity. Okay, so you guys can get that down. Here's a jump discontinuity, okay? It's a discontinuity that is not removable. It jumps, and remember, it's a vertical jump. We won't deal with horizontal jumps because there is more than just a hole at x equal a. There is a jump in function values that make the gap impossible to plug with a single point. Like if it was a f of a, I actually know, hey, that can actually come in and it'll work, no matter how we try to redefine f of a. In this particular thing, this has got a jump discontinuity on my function, okay? And it's the same. I just wanted to make sure it was there because I've been noticing when I've been copying my PDFs, this is not been coming up. My boxes, although I get rid of them, are covering everything, okay? Now, this is a function. This next one is an example of an infinite discontinuity or a vertical asymptote. They're the same. They're synonymous. Okay, or we'll talk about it as a non-removable discontinuity. The other ones were removable. This is non-removable, something I just can't do anything about. And we'll talk about removable versus non-removable in a little bit here. Now, in calculus, they'll talk about the continuousness of a graph, okay? If your graph is continuous on both sides of every point, and it becomes the same value for your y value, then your graph is continuous, okay? If the value of the limit of your graph from the left and the value of the limit of your graph from the right are two different values, it's not a continuous graph. And that's what we're talking about in this next section. The key concept from all these pictures is that we want the point x, f of x to slide smoothly onto the point a, f of a without any change in value, okay, without missing it from either direction. And that's when I was talking from the left side, from the right side. Okay, a function f is continuous at x equal a if from the limit as I approach a for the function f of x, the value at point A is actually f of a. I plugged that in. There's no issue with being able to evaluate that point at that spot. Otherwise, it is a discontinuous, it will be considered discontinuous at x equal a. And that's why these things are discontinuous, because as I approach a and the infinite discontinuity, it doesn't exist. As I approach a at the jump, it's not the same as the f of x of a here or f of x a coming from the other side. So that's what I got to keep in mind when I'm working with these values. Now, identify points of discontinuity judging from the graphs. Which of the following figures shows functions that are discontinuous at x equal 2? Are any of discontinuities removable? Okay, so I want you to look at it. I put in this earlier and it's not very vertical. We'll make a slight adjustment to that, or not. I'll just put it in again. There, it's a little bit better than the one that we had. It's not much. You don't come here because I'm an art teacher, trust me. Husen doesn't have any problem about his job. I ain't taking it anytime soon, okay? All right, so when we're looking at this, this is a infinite discontinuity, non-removable, okay? Does that make sense? So it's a vertical asymptote. So that's what I'm looking at, infinite discontinuity. It's a VA, and I'll write it down as a VA. Next, continuous graph. Continuous for all x. This last one here, if I got h of x, excuse me, my board's kind of behaving incorrectly. I'm going to see if we can get it fixed. So I've got h of x equal x minus 2, x plus 2 over x minus 2. Now what I just did was factor the numerator on top. This is an example of a removable discontinuity, what we'll end up calling a hole in my graph. Okay, because I can remove the discontinuity, I can remove when my graph in the denominator, what makes it 0, and when I can remove it, it means that's another factor above that becomes 1. Okay, so it's a removable discontinuity. It will create a hole. Now, I want to be clear about this. I actually say here that the hole is at 2, 4. Right now, I know there's a discontinuity at x equal 2. After I remove that factor where the discontinuity existed, that's why I can say it's a hole, because it's removable. I'm taking it out of the function. After I remove that factor, I take the x value of the discontinuity, and in this case, it was x minus 2. When that was 0, was at the value of 2. Well, I put 2 in to x, and I find out that my hole is at 2, 4. Okay, I can tell you the location of the hole. And that's important. I expect you to be able to do that on tests, quizzes, and your assignments. When you have a removable discontinuity, it's not just enough to identify it. You have to identify exactly its location. And all you do off the reduced function is you take that reduced function and place the value of x that would make that 0 in your denominator, and you put it in. Okay, so you have 2, 4s where your hole is located. Okay, and that's the whole story on that. All right. Now, when we're going through this. Discontinuities come from x values that result in divisions by 0. Okay, they make the denominator 0. If it's removable, it shows up as a hole in the graph. Okay, and that's just a circle above that point along the graph. If it's non-removable, it'll show up as a vertical asymptote. Now, when I have a hole, and I'm going to go back to the original, if I had a discontinuity and I didn't recognize it as being removable, okay, I was just checking numbers. If I go up to the top here and I talk about the fact that I didn't reduce it the way I did, and I'm looking at, well, you know, I've got x minus 2. It's got a restriction at x equal 2. If I do that, if I put 2 here, and I put 2 here, and I put 2 here, this is 4, that's 0, and that's 0 on the bottom. Okay, so this creates 0 over 0 for me evaluating the value of 2 that was a discontinuity. And some people, why is it a discontinuity? It's 0, but it's 0 in the denominator, and that's the issue. And also on this one, it's got a hole. If I evaluate 0 over 0, that's where my hole comes from. Okay, if I want to just know that, hey, it evaluated this and this is the result, what type of function is this? Removable discontinuity when we're talking about our discontinuities. Here, if it's a vertical asymptote, okay, and only a vertical asymptote, the bottom will be 0 and the top will be evaluated as some other value. Okay, that's what this is talking about. So I'm just wondering if the rule fits, and what I want you all to do is go ahead and look at these next ones and determine where the holes are located. I just love it when nothing looks the way I set up. Interesting. Okay, so this is one we just did. Okay, so I'm looking at this, and I've got my x minus 2 Okay, we'll see if this works. So I've got x minus 2, x plus 2, and this is x minus 2. And again, this is an example of what we just did. That's my hole, okay? And that's h of x. Matter of fact, if I wanted to graph h of x, if I put this in my graph in y1, and then I put my change, my new h of x into my graph, x plus 2, it should be the same exact graph. That's how I can check to make sure I reduced it correctly and found the hole correctly. Now, after I determine that, hey, it's got an issue at 2, I will have a discontinuity of my hole. Okay, I took that out. So I have a hole at 2, 4, and it's called a removable discontinuity. I have no idea why that's behaving the way it does. That was all written, so that should be gone. Hey, good. It is behaving right, kind of. Now, in this next one, there is no removable discontinuity. There is an infinite discontinuity with x minus 2. So I already know that this x minus 2, when it's 0, it can't be 0, so x is equal to 2. So I know my domain restriction on this, and my domain restriction here, if I'm talking about my domain, would be x can't be 2. Okay, if I talk about it as an interval notation, it goes from negative infinity to 2 and then 2 to infinity, but I'll leave it like that for this one. Here, I've got a vertical asymptote at 2 on this value. So now my domain, again, x can't be 2. My interval notation, that's my set builder. My interval notation from negative infinity to 2, and from 2 to infinity. And it can't be exactly 2 when I'm doing this. Are those making sense? Now, the extra examples. I want you to try in A, the 5A, Find the domain of each of the following, then find the discontinuities of each of the following functions. Classify them as a whole or a VA. Okay? Remember, wholes are removable discontinuities. VAs, vertical asymptotes, which are infinite discontinuities. So in A, I've got a factor first. I've got 2x, x. I'm going to go 2, 1. They're both negative. That's going to give me my negative 5x. And then I got x minus 2 on the bottom. Well, this is a removable discontinuity. Okay. Now, I've got it at 2. Not all wholes and removable discontinuities will happen at x equal 2. They'll change. Just happy coincidence here so far in our notes. So I plop that back in and I know it's 2, 3 if I'm doing this. So I know I have a removable discontinuity. I have a whole. And my function becomes f of x 2 x minus 1. So I've got a whole at 2. I got to find out where exactly. So I plop into 2 minus 1, so it's actually 3. So at 2, 3, I have a whole. Does that make sense? Now, from left to right on my function, other than at 2, 3, my domain's great. My domain, they asked me to find my range here. The domain's great. We're not asked to find range. So I have x cannot be 2. Or if I'm doing interval notation, I'm at the interval, I go from negative infinity to 2, union 2 to infinity. Does that make sense where I'm getting my information that I'm doing? They asked me to find the domain of each for the following, then find the discontinuities of each of the following functions, classify each as a whole or a VA. So I've got that done. Your turn, do B and C. Okay, so when I do this, keep in mind I've got a factor. So I got 2x, x, and I'm looking at it's going to be 2, 1. That's going to be positive, this is negative, and this is x minus 2. So right now I know I do not have a removable discontinuity, okay, because the factors are not the same in the numerator and denominator. I do, however, have an infinite discontinuity, which is a vertical asymptote. So I have a VA set up when x minus 2 can't be 0, so x minus 2 can't be 0 at x equal 2. So I got a vertical asymptote at x equal to, notice that's a vertical equation, vertical graph equation. And my domain goes from negative infinity to 2, and from 2 to infinity when I'm setting up that. Now, if I wanted to do it as set builder, keep in mind, set builder, x, this can't be 2. Now my last one, I got a factor. I get my factor going on. I have a whole at x plus 2. Okay, so now I'm looking at that and I get down to this. Please keep in mind my whole's at x plus 2. So in order to find the exact point where that hole is, I take my plus 2, which is x minus 2 now. I plop in negative 2, which is negative 8 up top, negative 2, negative 4, negative 8 divided by negative 4 is 2. So I've got my whole, I got my VA at positive 2, but my whole x equal negative 2 after I plug that in, that's all in the way. I get a negative 2, 2 is my whole. Are you okay with both discontinuities? One's a vertical, okay, and one's a whole or a removable discontinuity. Okay, those are the two that we've got in this one. And my domain, so I'm looking that over, I'm just going to do interval notation on. Are there any follow-up questions on this? And if you do ask one, I'll just repeat it so the people at home can do it. Every once in a while I forget and you hear a murmured question or some silence. I'd prefer that you guys actually hear it if you're watching from home. We're doing okay? Okay, sliding on. Now, kind of changing gears. We're talking about piecewise functions. Okay, for a piecewise function to exist, you have pieces of functions put together on a graph. Now, how do you know which function takes over at which time? I want to talk about the domain of the function, and that's what this is. X less than or equal to 0 is the domain for that part of the function. I like to have you guys think about it as you all are working at this part-time employed company. Okay, the graph is your place of employment. You are X minus 1. Okay, you come to work from negative infinity to 0. I know the work hours are really demanding. Okay, but you're coming in from negative infinity to 0. And while you're there, you're the person that's doing the job. So X minus 1, well, that's negative 1 and it comes down this way. So that's my function there. I have it colored in here at 0 because of the or equals. Okay, so this is my hours I'm working and this is who is working. Okay, now I have somebody come in and take over, right? Somebody different. It's not me anymore. I have X squared comes in. Well, X squared takes over at 0, but not exactly at 0. X squared comes in, starts watching what I'm doing, and then I work all that time, and then they go, okay, I get it. And then I leave and they take over. Well, at that point, it's open. And right at 0, parabola looks like this, but I will not use the left side of your parabola because it takes over at 0 and goes from 0 to infinity. And what I said in class, folks, is a parabola looks like this, but because the person comes in at 0, I won't use that part of the parabola. So we're looking at that when we're finishing out our piecewise function, okay? And we're just graphing it right now. So does it make sense from negative infinity to 0, my linear function had the work hours covered from negative infinity to 0, that X minus 1. As soon as 0 happened, X squared took over and went from 0 to infinity. Now, I have a jump discontinuity in this, right? Because I actually got to lift my pencil. It's not just a hole, it's a great divide I have to get to, all right? So that's a jump discontinuity here. I'm looking at the idea here that I've got jump discontinuity, it's non-removable, x equals 0. Now my domain is defined all the way along. I don't have a hole here. I have a value. If you say, hey, what's the value of the function at 0? I'll say, hey, it's negative 1. Okay, and then from there it takes over. And by the way, it's not 2 values, it's just 1. So it fits this idea of being a function. Okay, and then here I've got my range and I've got my domain. My range, however, has a jump. Remember, range goes from negative infinity to positive infinity. On the y-axis, my range is vertical stuff. So from negative infinity to negative 1, and then I have a gap. And by the way, that includes negative 1. And then I have a gap at 0 to infinity for my range. Okay, are you okay with what I did there? You okay with domain? You okay with range? Are there any questions, follow-ups? It is now your turn. Y'all try B. Y'all try B. I kind of give you some hints on the graph, so y'all try B. By the way, today we will be doing our piecewise worksheet on Monday. That covers this stuff. You might have a couple questions on your assignment in the book, but the main worksheet we'll do Monday. I am going to make sure we get to determining if a function is bounded or unbounded, and we're going to stop at maxima and minima. Okay? So you guys are graphing this. Make sure you get your graph going on. Think about what you've got. Think about it as from negative infinity to infinity, our company is open. You're a part-time employee. You come in, you do your job, somebody else takes over at that time, okay? You're not working from negative infinity to infinity. You get to have a break. You just go from negative infinity to 0 in this case, and 0 to infinity. That person that comes in at 0 just for that little interlude, boy, I wish I had their job, okay? Now, I got a linear equation. It's the same one that we just did, okay? It's open this time at 0, -1, because it doesn't have the or equals underneath. I have a person come in to fill in while we're switching, okay? They come in, they're kind of doing the job for a brief moment, and that's where I'm at 0, 1. Okay, that's my red part. And then x squared comes in and takes over from there and continues the job the remainder of the day. Okay, so because of that fill-in, I have no holes in my domain. My domain is defined from negative infinity to infinity. Okay, so I'm looking, I think I put it over here. I got that jump discontinuity. We talked about the jump, and I'm going to talk about my domain. Oh, there it is. I got a D right there. Mr. Boom, follow along. Okay, so I got my domain right here. Okay, and it's all real numbers, like I had said, because it's covered. I don't have any holes in my domain. But now, if I look at it, the vertical, my range, remember, the range is my y values, the vertical values. I go from negative infinity to almost -1, but I got a hole at 1. And now keep in mind, I know I start up here again at 0, 1, but my function starts at almost 0. So I kind of blow off that 0, 1 point because it'll be covered in the remainder of my range from almost 0 to infinity. So when I'm doing my range, I don't have here, I'm looking at the idea that I'm going from negative infinity and coming from the bottom, coming up, I'm going up from negative infinity to -1, not including -1, and I have a gap from -1 to 0, I don't count on, and I go from 0, around 0, to infinity and beyond, okay? Are you okay with where I'm getting my domain, where I'm getting my range, and how I'm graphing these functions in the interval that I'm given, okay? And these are called piecewise functions because pieces of different functions are combining together to be one. Y'all got C to see if we got it. Okay, I'm just going to leave this up to make sure people get it. You guys go ahead, graph C. See how you doing. Y'all got C. Just in case you drool when you're sleeping. Staying out late. Okay, remember, you're doing the function, you're graphing it. The graph stops when its interval is over. Just like you stop working when your time's up. Okay, so x minus 1, still the same graph, but now x is less than or equal to 0. So I get to talk about it being exactly 0 through there maybe. Okay, so I've got that dot at 0, 1 going on down to the left because that's where it exists. X squared minus 1. Now x squared is parabola. It takes over at x equals 0, but its first thing is -1 and it's open. So I take open there. Are you okay with this? Now what happened here is separately, okay, the first one, is okay, but I have a hole on the second one, but the first graph and the second graph combine to fill the hole, Okay, so I've defined that, and now I've got a continuous graph. My domain is from negative infinity to infinity, and my range is from negative infinity and infinity, no holes whatsoever. I can get that other range, but apparently I killed the domain. So we're going to put it, oh, there it is. Okay, so I got my domain, I have my range, I have no discontinuities in this piecewise function. Okay, are you okay with what I did with graphing? Are there any follow-up questions about it? Now, I know it says that we kind of went over yesterday, and I'm catching up on some stuff. Increasing, decreasing. Okay, from left to right, from left to right. So I start over here, and it's going up, it's increasing. From left to right, it's going down. Okay, from left to right, it's constant. Okay, every time we're talking increasing, decreasing, it's from left to right. Okay, just like we read, just like we do slopes, increasing, decreasing. There's something that the textbook does. It actually has boxed brackets, and it says, hey, it includes this. You can't have something increase and be constant at the same spot. You can't do that simultaneously. So that's why we want to make sure that we use parentheses in the domain values when we're increasing and decreasing. And remember, this is all about domain. Increasing and decreasing goes from negative infinity along the x-axis to infinity. Okay? We won't be talking about the range for increasing, decreasing. It's just along the domain, is it increasing or decreasing? Because we go from left to right. Okay? Now, we talked about those. I want to make sure you get that covered. Don't pay attention to that. We're doing one more page. Now, on this example, let's talk about increasing and decreasing. From negative infinity, as I go through here, this function is coming down like this. Do you see that? So it's decreasing from negative infinity to negative 2. It is constant from negative 2 to 2 because it's the same. It's a horizontal line. It's constant. And then from 2 to infinity, it is increasing. And that's how I represented it that way. Okay, so please write that down. Remember, we use parentheses, no brackets. The book will use brackets, and it's incorrect. I'm trying to get you ready for calculus, and the book made a mistake, and it stinks. Okay, so make sure you know that those are your ranges, and they're domain values. They're x values from left to right. Okay, and you look at increasing and decreasing in constant from left to right always. Okay. So make sure you get that decreasing constant and increasing down before you're moving on. I think I have something different in my notes than you do. Nope, good. So here's the deal. I just love it when it's not behaving the way I want it to. I'm going to tell you right now that's negative 2, 0. Okay, I want to be fair. And you can look at my graph. It's a parabola that has been slid left to negative 2, 0. Okay, that's the function. I want you to read decreasing. I want you to read increasing intervals. Remember, those are x value intervals. Okay, they're domain value intervals from left to right. What's going on with that function? Let's see if you understand increasing, decreasing, and constant. Go. So remember, from left to right, this function decreases from left to right, from negative infinity to 2. This function increases from that point up from negative 2 to infinity. So I should have those values coming out. Does it make sense? Are there any follow-up questions? And you got to understand, right at negative 2, I can't say including negative 2 and have it boxed in, because at that point it's decreasing and increasing at the same time. Okay? Depending on how I'm coming on my graph. That's why it's around negative 2 when we talk about it. This next function, I put in the asymptotes for you so you could see it better. Okay? They actually cross at 2 and negative 2 according to this, and if I was going to graph this, you know, work with it, x minus 2, 2 and negative 2. I don't know why I said that, but it's not 2 and negative 2, it's 1 and negative 1. But I want to make sure that what I got there is going to work for you all. So we're going to pull this up, and apparently I have it there, so I'm going to abuse that. Okay, are you okay with the values of my asymptote? Says I got one at x equal negative 1, I have one at x equal 1. And now increasing, decreasing, think about what it looks like and think about where they're located and go for it. Okay, go left to right, left to right. Okay, think about what it is, left to right. So from left to right, left to right, from negative infinity to 1, I'm increasing. From 1 to 0, I'm increasing. Okay, so I got my increasing there. From negative 1 to 0, I'm increasing. From negative infinity to negative 1, I'm increasing. Okay, now decreasing. I'm decreasing from 0 to 1. I'm decreasing from 1 to infinity. So I got those going on. No idea what's going on there. That looks dumb. So from 0 to 1, and from 1 to infinity. Okay, you're all right with that. You got my vertical asymptotes on. I know that. I didn't have any here. I could talk about my VAs being x equal 1 and negative 1. I should probably fill that in for you all about why I know what I know. Are we okay with increasing and decreasing? Remember, it's all about the domain values. It's all about the domain values. Okay? Now, boundedness. When I'm looking at boundedness, what do you have? Yep, go ahead. Okay, thank you, sir. No, that's right. Okay, so we have boundedness. Not bounded above, not bounded below, because there is no restrictions. This keeps kind of going up here, that keeps going down here. Okay, not bounded above, they keep going up, but it's bounded below. There's actually a lower extremity. We can actually talk about that absolute minimum on that graph. And here, bounded above, but not bounded below. So we'll talk about things being bounded above. Not bounded below because it keeps going, okay? And we can talk about the maxima that we have here. And these be relative max if they're the same. And in this next one, this is a bounded function, okay? So we'll be looking at it being bounded itself because it doesn't go to infinity on top, it doesn't go to infinity below. And that's it. We're gonna cover it there. But boundedness is range. Now, please keep in mind, boundedness is about the range of the value. Okay, so there's a difference between increasing and decreasing, where that's all about the domain. But boundedness, if you're looking at the range of the value, does it stop or does it does it keep going, or is there a restriction on how high it gets? Nice job today.